welcome to Living Mirrors with Dr. James Cook. My guest this week is Karl Friston. Karl is a theoretical neurobiologist and Professor of Neuroscience at University College London. He's also an honorary consultant at UCL's Queen Square Institute of Neurology and is a fellow of both the Academy of Medical Sciences and the Royal Society. He's also the world's most cited neuroscientist. As an undergraduate at Cambridge, he studied natural sciences with a specialism in physics and psychology and went on to train as a psychiatrist. He first rose to prominence after inventing multiple techniques for analysing brain imaging data, and later turned his attention to developing a unified theory of the brain, the free energy principle, which is what we talk about today, alongside consciousness and psychedelics. Hope you enjoy the conversation. Okay, I'm here with Karl Friston. Karl, thanks for coming on the podcast.
Well, thank you very much for having me.
So we're going to be talking today mainly about the free energy principle, and I thought perhaps we could begin with its origins. I'm interested to know, did it come to you as a kind of moment of sudden insight, or was it a gradual process of refining the ideas?
It was very much an incremental process of refining the ideas. The intuitions I think we all have, and certainly the sort of the fundaments of what one would like to explain were in place. I would imagine when I was in my adolescence, but there's been a long journey of formalizing those ideas and finding the right calculus, the right maths, the right sort of constructs and ideas out there in many different fields, but specifically in sort of maths and physics that lent a crispness to the ideas of the sort that you would be able to, articulate the ideas to the academic literature and also provide proof of principles, either mathematically or through numerical analyses. So that's taken many, many years. I think I'm now over 60, so it's taken many decades to get there.
And then in your kind of career as a neuroscientist, did it start as an explicit attempt to kind of, as a neuroscientific theory, a theory for the brain, and then you realized its kind of wider applicability?
Yeah, that's absolutely true. And in fact, even more pragmatic than that. So, that calculus, the mathematics that underwrites the free energy principle, actually inherits from having to contend with the problems faced by any sentient being as a neuroscientist trying to analyze neurobiological time series, in particular sort of imaging neurotime series. Exactly the same problems confront you when you're trying to infer the hidden causes of your brain imaging data or your electroencephalographic data that present themselves to you and me when we're trying to make sense of our visual data and all the other auditory and interoceptive streams. So I had to become fluent in inference and making the most of data, sense making in a very practical context. And then it was an easy move to say, well, perhaps the brain is also solving the problems in this principled mathematical way. Indeed, all the empirical evidence speaks to the brain and its functional architectures as essentially being a little scientist doing exactly what we were doing. So that more than just is this a theory of how the brain works, it actually inherits from the practical application of mathematical ideas to working out how the brain works, looking at empirical data from the brain. But certainly the underlying ideas were originally more generic. It was trying to solve the problem of self-organization and sort of the existential imperatives for things that we see around us. And of course, the most interesting thing is me. So clearly, me and my brain were sort of top of the list in terms of explanatory targets. But from a maths point of view, there is certainly something special about the brain. But the fundamentals have to be translate to any domain of self-organization. So there has been an effort in the past decade, and more so over the past 5 years, just to say, well, look, the brain is a beautiful example, a fantastic organ, but the principles by which it operates are shared by any fantastic creature or structure, from a virus to a vegan.
Yeah, I mean, that's a great correspondence that you had it in your day-to-day work, because, everything we're going to be talking about is kind of relevant to the Bayesian brain hypothesis, right? This kind of, and for, it's good for people to keep in mind this idea of the brain being kind of hidden in the skull, and it needs to be doing this kind of hypothesis testing, right? As you say, it's like a little scientist taking clues from the senses and building hypotheses, predictions, models of what's going on in the wider world.
No, absolutely. That was beautifully put. Yeah, that's exactly what the theology principle says. Yes.
Great. So, would it be possible to try and give a kind of a summary of the free energy principle, and then we can unpack it in more detail?
Yes, of course. So, when asked to do this, I usually ask whether you would like the sort of the high road story or the low road story. So, I think there are two routes to an intuition behind the basic idea. You can either take a sort of low road, which is a bottom-up road, and sort of start from the ideas of the students of Plato through to Kant and see how they unfolded in the 20th century in terms of ideas like analysis by synthesis, epistemological automata, perception as hypothesis testing, right through to modern day machine learning, deep learning, and nods from that community, the machine learning community, from people like Geoffrey Hinton and Peter Dayan, to the neurosciences and to brain in the sense of things like the Helmholtz machine. Helmholtz being a very key figure in that pedigree, in that legacy of thinking, where it's all about, effectively, just as you've said, the brain as a scientist, trying to make sense of data by forming fantasies, beliefs, hypotheses that best explain the data at hand. And then the data now become, or the senses, the sensorium is now just in the service of either confirming or disconfirming a particular belief about states of affairs out there beyond the sensory veil or beyond the skull. So that story has been given an important twist. That twist has always been there, from the days of things in engineering such as cybernetics and Ross Ashby. It's been there from the point of view of ethology in terms of Gibsonian affordances, but the twist I'm talking about is an enactive turn, very much a pragmatic turn at the beginning of this century, where people were more focused on the situated aspects of that inference. So it's not just about extracting information from sensory data. It's not a sort of outside-in process. It's much more of an inside-out process, where you're in charge of soliciting the data that you need to confirm or disconfirm your hypotheses. So that inactive part is reflected in things like the 4 E's, extended, embedded, and I always forget one of the 3, so I won't attempt the full 4, but embodied and extended. So very much coming back to this sort of meme as the brain as a little scientist, you think about what the scientist does. I mean, he actually spends a very, very small amount of her time analyzing the data, but much more time designing the experiments. So that would suggest that we're talking about an inference process, fully described, I think, in the writings of people like Helmholtz and Richard Gregory, perception as hypothesis testing. But on top of that, there's all the machinery that prescribes those principles by which we go and solicit and garner the right kind of data, in exactly the same way that a scientist would spend most of their time writing research proposals, thinking about the experimental design, getting that experimental design exquisitely correct, so that the data that is disclosed by that paradigm has the greatest power in terms of disambiguating between this hypothesis and another hypothesis, usually the alternate hypothesis and a null hypothesis. So that takes inference and the brain as a fantastic organ, a purveyor of fantasies, hypotheses, to a new level. So it's now not just about making sense of the data. It's really, how would I go and solicit? How would I palpate the world in many, many different ways? Whether it's attending to different gut feelings, whether it's literally palpating my fingers or moving my eyes, visual palpation. All of this has to be now understood in the service of optimizing inference, in the same way you have to understand how a scientist works in terms of designing the right kind of disambiguating experiments. So what we are talking about is basically action. So, hence active inference being the sort of teleological corollary of the free energy principle.
Right. Yeah, I'm very I'm a proponent of the embodied view, I would say, because in the first instance, when I described the brain as this thing that's really separate, it's hidden inside the skull. It's, the brain as a computer or a detached scientist, and the world is all the way out there, and these clues are coming in. That's one way of thinking. But then, as you say, I guess another way of thinking is, well, really, we're a body, we're a living thing that has a brain. The brain is in service of this process, but we are actually really situated in a world. We're not really detached, truly separate from the world. And I think that's an important shift in perspective that the free energy principle really provides.
Yeah, absolutely. And so many thoughts are kicked off by that observation. The circular causality, the exchange with the environment, absolutely crucial. The generalization of these notions beyond the brain, of course, as you note, extends to the body. So our body is also, in effect, a model of our lived world in a very real sense. For a trivial example would be the wavelength sensitivity of photoreceptors in our retina. That are perfectly tuned to the wavelengths of ambient light from the sun. So, not only are we optimized in a normative sense, or put it another way, not only do we optimally infer what's going on in terms of our neuronal dynamics and our brain dynamics, but our evolutionary dynamics, the evolutionary trajectories that has equipped us to sample the world in the right way, to perform those experiments with the right measurement tools, is also provides an essential context that enables our brains to work. And of course, our bodies are the thing that enables our brain to work. And ultimately, of course, so is the environment. And then the other thought that you kicked off, that things get even more interesting from that sort of slower timescale, that evolutionary perspective, when you think that we actually build our own environment. So, the notion of eco-niche construction. So not only are we in charge of deploying our sense organs to get the right kind of data, navigating around the world, looking here or looking there, or choosing which news channel to watch or which Wikipedia page to go and forage on, that we also we are also in charge of constructing the world that is supplying that information. So we build rooms with straight edges because they provide unambiguous evidence, and we inhabit worlds where somebody has built traffic lights and that are burgeoning with deontic cues. So there's really important circular causality going on here. Multiple time scales and spatial scales, but also that transcends what's on the inside from the outside. The other train of thought that question sparked was bringing us back to the high road understanding of the free energy principle, which is does not rest upon all the great thinking about sentience over the millennia, but inherits much more from the point of view of the physicist, just asking, well, look, you've got this self-organizing system. What features or what processes or what mechanics must it possess to remain in a self-organized state. And when one pursues that sort of high road to the free energy principle, which would be the physics of self-organization technically to a non-equilibrium steady state. So this is 21st century physics, not the kind of physics you did at school, which was all about equilibria. This is really asking the question, if you were dealing in school with thermodynamics, you'd be talking about idealized gases in a heat bath or a heat reservoir. Nowadays, people want to know, well, where did the heat bath come from? So for us, that's our sensorium. How do we differentiate between the gas and the container, and what contains the container? So all of these issues, which now transcend equilibrium physics, are the province of non-equilibrium physics. So there's a lot of really interesting, I was going to say complicated, it's fairly straightforward mathematics that we understand about the mechanics and the dynamics of systems that have some separation in play. And then technically you have to ask, well, how would you define the difference between, say, brain states and outside world states, or between sensory states and active states? And of course, as soon as you conceive of this carving up of different states of the universe into things that are possessed by a person or a particle, and things that are not, things that are on the outside, you're now obliged to consider the two directional coupling between the inside and the outside, which brings us back again to the embodied aspect. Our brain is embodied, our bodies are immersed in a world which we actually make, and also has to transact with other embodied creatures. So all of these boundaries that define these bodies, these particles or people or plants, require you to understand how they are, or how they mediate the reciprocal two-way coupling between the inside of any body or particle and the outside. So that sort of, that embodied aspect really hits you in the face when you start to look at the maths of this thing. And that's where most of the interesting, if you like, derivations, that's where the mechanics emerges from. It's just having this partition into states of a thing, particle, plant, person, the states of nothing or everything else, and crucially, the states that separate the two. So technically, these are the Markov boundaries, or the Markov blanket that enshrouds our body or our brain and enables us to separate me from not me. So that is the sort of the high road that you would get to the free energy principle, which, in a couple of sentences just says that, well, here's a system, it's self-organized to occupy a particular set of states that it could occupy, and that those states now characterize that kind of particle, creature, plant, whatever you're talking about. In the presence of the separation of the states of the thing and everything else, there has to be a certain dynamics, a flow of states, trajectories, paths of states that the system would take, formally identical to things like the path integral formulation of quantum electrodynamics by Richard Feynman. And in fact, using exactly the same maths, you can then show, well, it must be the case that in order to these states to gather themselves up and live within these restricted domains, regimes of state space that mean that I am a certain temperature and I am me. It must be that the states are flowing towards the regimes that have the highest probability of being in that state, given I am me. So that's important because if I was a statistician analyzing my brain imaging data, that quantity, or the logarithm of that quantity, the logarithm of the probability of being in this state given I am me, is known as model evidence, where me is the model of the world. So now you have a very succinct if somewhat poetic, description of the behavior of any system that exists, in the sense that you can separate it from its universe. It will always look as though it's trying to maximize the model evidence. And technically, it's a Bayesian model evidence. And then you get this notion of self-evidencing, that just to exist is simply to make moves and to have dynamics that look as if they're trying to maximize the evidence for your embodied model of the environment in which you are immersed.
Right, that was a great summary, and there's lots of different things we could focus on there. So I'll try and unpack it again from the beginning. We're beginning with the high road and this view of thinking in terms of the thermodynamics of life, right? So as you were saying, you're thinking in terms of systems that exist. And I like that you use this word exist, because I think the etymology is it means kind of to stand out. So it's this thing that's relatively separate from the background. It's done something to be worthy of being called a separate thing. And that thing that it must do is to assert a boundary, right? It has to decouple itself, as you say. That can be described as a Markov blanket statistically. And then because of the second law of thermodynamics, because you've got these constant random fluctuations, parts of that boundary have to sense and parts have to respond, right? To react and keep yourself together over time. Otherwise, you're just going to fall apart like everything else. But in order to do that, you need to build these models inside. You can't just, if I sense that there's fire on my skin and then I react, it's too late. You need to be predicting ahead of time, right? You need to be building these anticipatory models. And then from that picture, you get this really powerful tautological reasoning. I can't think of a better way to put it, that I find very satisfying, of similar to natural selection, systems that are good at surviving, systems that are good at doing this trick of self-perpetuation, they survive, they self-perpetuate. And I find that exhilarating, and it provides a really deep insight. And I remember after hearing about natural selection in school as a teenager, I was walking by a canal and I saw a bird. It was kind of flying, and then it landed on the water, and it used its kind of webbed feet to slow itself down. And I was just struck kind of really vividly by this. When you said that the body or the organism is a model of its environment, I was struck by this feeling of like, well, all that is the process of life manifesting in that niche. There's air and there's water, in the same way that a fish swims with these kind of fluid dynamics. I was struck by this very odd realization of just all life is just things modeling their niche. And I feel that falls out of this insight as well. But when it comes to the tautological reasoning, in the sense, as I said, of things that survive will survive, I'm assuming you share the feeling that that's a very powerful way of thinking. But I think a lot of people, if the penny doesn't drop, there could be a feeling of why are you saying such an obvious statement that seems to carry no insight.
Yes, no, again, that was wonderfully put. And just before I forget, you may have to remind me what question I'm responding to here. But I didn't know about existence being standing out, but that is great, because it is the whole point of a Markov blanket is to identify those internal states that stand out from the external states. So the standing out is if you like, the existence or the raison d'etre for the mechanics that inherit from the Markov blanket, which is the standing out. It's the thing that enables you to discriminate between one state and another. Sorry, now I have forgot what you.
That's quite all right.
What was the last thing you said?
So it was on the kind of the tautological reasoning, things like natural selection and finding them powerful explanations.
Well, it's very comforting to hear that you like that, because I certainly like that, and the beautiful simplicity, which is exactly the same as a sort of tautology of natural selection, which of course once you've had that, then there's a lot of demystification, and one moves a little bit closer to Quine's desert landscape in terms of understanding, explaining the nature of things. And this is exactly what the free energy brings to the table. So I use the word deflationary a lot, because I think there's a tendency to burden really quite simple dynamics with a teleology which obscures the simplicity of what's underneath the hood. Simply existence, will in itself be a sufficient description of a system that supplies everything you need to know to say, well, then this system, because it exists, must behave like this. And then you can put the teleology on the behaving like this, but there's no need to. So there are loads of questions or aspects to your question which would be great to pursue. I'll just focus on a practical one, but I'd also just like to link what you've just said to, in terms of sort of the fish swimming through water, or the duck, really efficiently using its paddles as water breaks. That thinking, I think, underwrote very much the cybernetics movement in the sort of the first half of the last century. And I'm thinking here particularly of great thinkers like Ross Ashby and Turing, who actually knew each other and were talking about these things in a little club called the Ratio Club, which was housed effectively in UCL. They used to meet in the basement at Queen Square.
Oh, wow.
Yeah, and people, I think actually, Horace Barlow, as a very young man, might have been in attendance at some of the later meetings before Turing died. Anyway, I get distracted. But one of the things that came out of that style of thinking, and particularly Ross Ashby, who would, certainly in Europe, is seen as the father of self-organization, along with Wiener cybernetics, came out with this notion of the good regulator theorem, which is very closely related to the duck example, that in order to navigate and to successfully exist or survive in a particular world, you have to be a good model of that world. So this is beyond having a good model. You are that model. So any system that successfully manages to regulate its world must be, and this Ashby purports to have proven this mathematically, it must be a model of that world, which brings us back to the importance of embodiment, and also appreciating that existence is not just me existing in the moment and trying to remember what we're talking about, but also at an evolutionary time scale, the same laws just apply. The thing that I forgot was well, if it's so deflationary, if it's just a statement which is so simple, things exist and existing things move towards the states that define their existence, why bother? It's a good question. There are answers to that question there, because if you can write down the mechanics, let's call it a Bayesian mechanics, that comes from a Markov blanket that itself is the definition of existence in the sense of standing out. If you can write down the mechanics, what you can then do is turn that on its head and write down the states, and then you can solve the equations of motion and the mechanics and the dynamics. So why would you want to do that? Well, you might want to do that if you wanted to model or simulate or create either a real world or in silico artifact that be formed in the same kind of way as either very simple creatures or self-organizing particles. For example, a thermostat would be a very simple example, and then probably the most complicated example would be you or me. We can talk about what defines the difference between a thermostat and a virus and a vegan later on. But the key point is in terms of what does the free energy principle bring to the table, above and beyond a satisfying deflation and the joy of the tautology you get with natural selection, is the mechanics, that the mathematical equations that allow you to simulate sentient behavior. from first principles. And then you might ask, well, why would you want to do that? Well, if you wanted to build generalized artificial intelligence, either purely in computers or actually physically realized, you would need to be able to do that. If you wanted to model aberrant active inference in the service of understanding abnormal beliefs in psychiatry, for example, so where you construe false inference or inference that is not fit for purpose in relation to the world you're making inferences about as psychopathology, then there's an easy road to understanding inferring things are not there when they are, would be exactly a description of agnosias and neglect syndromes in neurology. Inferring things are there when they are not is a description of hallucinations and delusions and some of the positive symptoms of, say, schizophrenia. So you've got now a calculus and a first principle account of a realization of that calculus in terms of simulating sentience that you can now use to try and understand and model psychopathology and psychiatric and neurological disorders. So there are two very practical applications or reasons that you might want to understand the basic equations, the basic mathematics that come from a very deflationary place, that are almost tautological in their construction, but they just describe things that exist. And if you are dealing with a modeling and want to build things that exist of a particular sort, then you will need to know that mathematics. So that's why we do it, or that's why I do it. It's the free energy principle and the pure theory is really a backdrop to motivate applications, usually in sort of computational neurology or psychiatry on the one hand, and then on the other hand, find some or have in place a first principles account that will help people in machine learning and active inference and other domains, including, for example, the current coronavirus outbreak. Knowing how to make the most sense of the data. It brings us back to the what you have at hand is a mechanics that describes a good scientist. So whenever you're put in a situation of being a good scientist, then you can now recourse to those basic principles. And I mean that in a really practical sense. I suspect we're going to come on to, I repeat, the difference between a virus and a person. That difference will rest very much upon for inferring what I'm doing, and in inferring what I am what I'm doing, I have to work out what is the best thing to do next in terms of reducing or optimizing my inference and resolving my uncertainty, very much like designing the best experiment.
We have this picture of living systems minimizing their entropy, keeping themselves ordered, and we also mentioned how this kind of necessitates the building of models to anticipate what's going to happen and respond adequately. And one of the things I find really exciting with the free energy principle is it seems to offer a way of bridging these two aspects, where on the one hand you have a real thermodynamic system, a physical system, and on the other hand you have models, information, and we use different language to talk about these two things. But there are two types of free energy. One that each seem to live on either side of this divide, but they relate to each other. So perhaps we could maybe describe what they are and then unpack how they relate to each other.
I see. Yeah, no, absolutely. So I guess what you're talking about is the distinction between the thermodynamic free energy and the variational free energy that speaks to understanding dynamics in terms of probability distributions. And you're absolutely right. They are they describe different things. They are formally equivalent in the way that they are constructed mathematically, but they refer to very different probability distributions. So perhaps the simplest way to understand the difference is in terms of what is a free energy. So a free energy is an interesting construct. It's if you like, it's a relative entropy that's equipped with an additional term, which is an energy term. So to be a free energy, you have to have an energy and an entropy, basically. And then you ask, well, what is an energy and what is an entropy? Now, the entropy is easy to answer. It's just the shape of a probability distribution, a probability density, which could be over continuous variables. It could be like a sort of bell-shaped distribution, or it could be over discrete, say coin tosses. It could be sort of 50-50. These are examples of probability distributions and densities, respectively. And the entropy just scores the average uncertainty in these distributions. If it was a bell-shaped distribution, a very wide dispersed distribution would have a very high entropy, a very confident, very precise belief. Sorry, I've used the word belief prematurely, and I'll explain why in a second. A very small entropy would give you a very peaked distribution. What about the energy bit? Well, it so happens that you can, if you just drill down on all of physics, whether we're talking about quantum mechanics right through to classical mechanics, entropies are basically log probabilities, the logarithm of a probability, so that the probability can only be sort of between 0 and 1, say, but the logarithm can go from minus infinity to plus infinity. So the log of a probability is effectively an entropy. You may know it as a potential, for example. So both the bits that constitute a free energy are really attributes of a probability distribution. If you now condition that probability distribution on something, for example, me having a probability distribution, or my internal states, or a gas, then those become conditional probability distributions, and you can start to call them, in certain circumstances, Bayesian probability distributions or Bayesian beliefs. So now what you've got is a single number, a free energy measure of beliefs, and the question now is, well, what kind of free energy is? What kind of free energy are we talking about? Reduces now to specifying what particular probability distributions you're talking about. So if you're talking about thermodynamics, and I should preface this by saying that the maths is identical, that the functional forms of the equations are absolutely identical, and also all the names are identical, but there's a profound difference between the kinds of probability distributions that thermodynamic free energy and all the attending thermodynamic constructs like enthalpy and energy and potential talk about, and those that are slightly more general in the sense they just apply to distributions over states, and in particular sort of internal states and external states once you've got this Markov blanket in play. So the difference between, well, let's just take that as an example. The difference between the variational free energy that we are talking about in relation to building models of the world and inference pertains to probability distributions over external states of affairs, whereas the thermodynamic free energy would pertain to the actual distribution, say, of neuronal activity that is encoding those external states of affairs. So that fundamental difference is a difference between the probability distribution of something, say my neural activity, or a gas in some container. So I've got my neurons in my skull, or a gas in some container. The distribution of the different states of my neurons in a skull, or atoms or molecules in a container, that would be the thermodynamic entropy. And usually speaking, systems like you and me minimize that. They try and resist the second law of thermodynamics, so that we don't dissolve, dissipate, decay, and all those horrible D words, including death. That's not what the variation-free energy is about. The variation-free energy pertains to a distribution, a belief about external states that's encoded by the internal states. And there, interestingly, you want to maximize the entropy. You want to keep your options open. You don't want to commit to a very precise belief or a very precise hypothesis or fantasy about what caused these sensations. You want to give yourself a bit of wriggle room, a bit of latitude. You still want to have quite an accurate prediction or account of the sensations and to be able to predict them. But you want to do it in a way that is as simple as possible, in accord with Occam's principle. Therefore, you're trying to minimize your free energy by maximizing the entropy. So this speaks to an easy paradox if you don't understand the distinction between the informational, the variational free energy, and the thermodynamic free energy. In minimizing the variational free energy, remembering that free energy is equal to energy minus entropy, you're maximizing the entropy, keep your beliefs as accommodating as possible. Whilst the concomitants of that, from the point of view of the thermodynamic free energy of the states of the brain, for example, or your body, that are encoding, standing in for, parameterizing these beliefs about the external states, they will generally be subject to a decrease in the entropy. So that sort of opposition between the thermodynamic free energy and the informational free energy is absolutely crucial to this sort of mechanics of self-organization and sentient behavior. And as you rightly point out, the free energy that we're talking about is applied to beliefs about things. It's not the information inherent in the behavior of a gas or a bunch of neurons. It's what that particular configuration of the gas or the bunch of neurons encodes or parameterizes in terms of holding beliefs about the outside.
Right. And is it accurate to say that the process of minimizing the variational free energy is equivalent to minimizing prediction error or surprise, these errors in your models?
Yeah, under simplifying assumptions, the variational free energy just reduces to a collection of squared prediction errors in exactly the same way that, if you've ever done a t-test, for example, you're just trying to find the difference in, say, two group means from two bunches of data that minimize the residual sum of squared errors. So, the simplifying assumption is actually quite an important one. It's just that all the randomness, all the uncertainty is well behaved, in the sense that the random fluctuations conform to Gaussian probability or bell-shaped distributions. And I mention that because that's such a ubiquitous and commonplace assumption, and probably a veridical assumption, that nearly 90%, if not 99% of statistics is based upon that same assumption. That's called parametric statistics. And in that, under those parametric, normally distributed or Gaussianly distributed random fluctuations or effects, then you can always articulate the free energy as basically the squared residual errors, prediction errors, and then you can go off and talk about predictive coding, predictive processing as prediction error minimization. Technically, what I've taken to sort of iterating in more technical discussions is that you can always write down a free energy gradient as a prediction error, even without that sort of parametric assumption. Why is that technically important? Well, if you remember from the higher the physics perspective on self-organization, we're talking about flows through some abstract state space that now we've carved up, using our Markov blanket into stuff on the inside and stuff on the outside, and these flows basically are downward flows on a potential function that just is the variational free energy. So it's just like a marble rolling to the bottom of a pudding basin, finding its minima, looking as if it's aspiring to the most likely, the minimum potential, the maximum evidence, the self-evidencing optimum, which is at the bottom of the pudding bowl. But what's actually in play from this deflationary tautological account is just a potential minimizing gradient flow, which means all you need to know to either describe neuronal dynamics or indeed the kinematics of your body, or what you secrete or where you look. All you need to describe or simulate are the free energy gradients, the potential energy gradients, if you like, from the marble in a pudding bowl metaphor. So the free energy gradient prescribes, defines, and quantifies the dynamics that underwrite the self-evidencing and the inference and the predictions. Therefore, it is important to know that a free energy gradient can always be written down as a prediction error, which gives greater license to those people who want to talk about predictive coding and predictive error minimization. You can go beyond Gaussian assumptions to do this at the level of these fundamental gradient flows.
Right, but I think it also gives insight into maybe the strategy that the organism is employing in order to keep itself alive, keep itself surviving, because it seems to me, you show this equivalence between minimizing the free energy basically being the same as minimizing, prediction error, how surprised you are by mistakes in your expectations, and that relates to this process of minimizing your entropy in the kind of this thermodynamic sense. And so, it seems to me that you've got an account here of, if you think it shows that if you behave in such a way as to keep trying to, with this kind of confirmation bias, trying to seek out a way of being in the world where you're not being surprised, that's going to keep you alive. And there was in one of your papers, there was a line about, I think it was the long-term average of surprise being the same as entropy. And it's kind of stated mathematically, but I was thinking it through conceptually, and I was like, well, like a system that is constantly caught off guard with constant surprises, that's a system that's not going to survive very long, right? If it's not modeling its world accurately, if it's not predicting its world, it makes sense to me that it will end up with all the D words that you mentioned earlier.
Yes, and you've taken us very gracefully now to to the distinction between applying the free energy principle in the moment to derive things like predictive coding for sessile creatures that don't have to move around. And then moving from that sort of very simple predictive coding world into the world of active inference, where we've come back to action and embodiment and making moves on the world. So we're now back to the brain as a scientist who's not just caricatured as analysing data, but the other half of her job is designing the experiments and making moves in the world to generate those data. So now what you're effectively saying is, well, what are the first principles that I would go to in order to find the best way of behaving? So now it's not trying to make inferences about states of affairs out there currently generating my sensorium. It's now, what am I going to do next in terms of attending to this or attending to that, or looking over here or looking over there? So now you need a whole new set of principles, but of course, pursuing this deflationary account, they should all inherit from the minimization of surprise or free energy or prediction error. So what you're saying is, what would I expect to happen if I made this move? So what would my expected prediction error be, or my sum squared prediction errors, or what would my expected surprise be? Well, what it is exactly as you've said, it's called uncertainty. So mathematically, the average or the expected surprise of an event before you've seen it occur is just the uncertainty, it's just the entropy. So if I want to minimize surprise in the moment, surprise about what I have just seen, then I just change my mind so that now that makes the most sense. If I change my mind, so it's like that, that explains what I've seen now. That would be minimizing prediction error a la predictive coding. But if you now want to decide how to act upon the world, how to self-evidence in a truly enactive way and embodied way, you now have to not deal with surprise, but the surprise I would expect if I did this or I did that. And that's where the uncertainty comes in. So what you said is something quite fundamental, that on that account, to minimize the expected free energy, the expected surprise, we are necessarily going to be curious creatures. We are going to selectively commit to those courses of action that resolve the most uncertainty. Mathematically, that's exactly the same as soliciting that kind of sensory consequence of my action that has the greatest information gain. Say I saw a fluttering in the corner of my visual field, and I had a whole bunch of hypotheses of what could have caused it. It could be an insect, it could be a little bird, it could be a leaf. I know, though, what I do know is if I looked over there and foveated that the source of that stimulation, I could resolve my uncertainty. So I know with certainty that I can resolve my uncertainty conditioned upon that particular action. So that's the essence of active inference. And it's all about, actually, in a sense, it looks a lot like surprise seeking. That's not true. It's more sensation seeking in the service of seeking information and resolution of uncertainty. So you've got this sort of information seeking like imperative built in to the surprise minimization construct, but only, if you like, is realized when you think about the hitherto not observed consequences of action. So action now really underwrites all of this sort of, if you like, move from a sessile organism to something that can actually move around, and has to decide how to move, what its best moves are going to be.
Right. And I think for understanding these survival strategies, it's important to remember that we exist as these open systems that are kind of inherently complex, right? And you were mentioning at the start how we move between a certain number of states. So I breathe in and I breathe out, and then I keep doing the cycle, and then I move between these two states again and again for the entire time that I'm alive. And if I were to just stay in one state, then that would be a state of being in equilibrium, right? I would dissolve into everything else. So I need to be doing an active process of shuffling around my states as a kind of survival strategy. But then within that, a kind of subsequent survival strategy, if that's not good enough, well, I can't do it blind, I guess. I need to have these expectations and then adjust based on the feedback. And I think it's also worth mentioning that, when we're talking about expectations, we're talking statistically here, right? Like a fish. So like a fish expects to be in water because it finds itself in water, and it makes sense. The way I think about it, is it makes sense for it to keep expecting water or to return to water if it finds itself out of water, because the fact that it exists in that niche shows that it's a successful strategy to some extent, so it's wise to continue to expect to feel water. And if you don't, then you should probably, move back in the direction of water.
No, absolutely. Yeah, that's a lovely example. Um, so it actually reveals two sides to this expected surprise. And I should say you're absolutely right. I'm often guilty of using words in a very technical sense, a mathematical sense, without realizing that they're heard in a folk psychological sense. So, when I talk about a belief, I'm talking about a probability distribution. I am not at this stage in any way intimating a propositional belief or a personal belief. At best, they could be subpersonal, beliefs held by a receptive field, in the visual cortex of the brain. Similarly, with expectation, this is not a propositional expectation about what might happen in the future. It's a mathematical averaging operator. So it's if the surprise of something, technically the self-information or the potential that we were talking about for the negative log probability of something happening, is an attribute of something that you've observed that has actually happened. If something hasn't happened because you haven't actually acted yet, then you can only estimate that that thing only lives in expectation, or on average over all the things that could happen, all the outcomes that could happen. So that's a kind of expectation. So it's more like an anticipation from a sort of a more natural way of describing these things. And you're absolutely right that that kind of anticipating what would happen if I did that becomes absolutely crucial for survival. I'll just make a little sort of note in parentheses here that we've moved with gay abandon to talking in a very teleological sense. We must always remember that underneath, this is the way systems have to behave. It's just a description of the way that things behave. So often articulated as, it looks as if. So, but certainly when one moves from these gradient flows in the moment, that would be apt to describe things like predictive coding in the moment, or the even to extent the behavior of a thermostat that can actually act on the world by turning on a heating source or not, but it's all in the moment. This is a mechanics which is trying to describe gradient flows in the moment. What we've done now is really talk about trajectories into the future. So mathematically, this is akin to the pathological formulation, where we're talking about sort of expectations or averages in the future. And of course, that future can be quite can have quite a distant horizon. So what we're now talking about is planning. Nothing more or less. Some creatures plan. Thermostats don't plan. Viruses don't plan, but they still conform to the free energy principle in the sense that in the moment they're always avoiding toxic concentrations. Or if you're a fish, and you have the opportunity to go back into the water, then you will do that in the moment. You don't plan to do it, you just do it reflexively. And you can get quite a long way describing biotic self-organization and many simple creatures simply through this in the moment kind of minimizing your prediction error or your surprise or your free energy. What we've done though is look at other kinds of systems that look as if they are planning. And we're now talking about the probability distributions, not at the state at this moment in time, but over the paths into the future. And this is where all the interesting, I think, aspects of active inference come to the fore, that come now with the temptation, which we will succumb to put a teleology on them. I've done that just by saying planning. Let's do that, having qualified the fact that, so whenever I say certain systems plan, what I mean is they look as if they're planning simply because they are that kind of system, they have that kind of generative model. But that planning, avoiding surprises in the future, has two aspects to it. I was emphasizing this sort of epistemic affordance, this the drive to curious behavior, the things that make us curious creatures. the resolve uncertainty, which is just the expected surprise. But there's another pragmatic part of that, which speaks to the sort of the fish trying to get back. If the fish could plan and it could choose, it had a choice. It could press that button or that button. That one takes it back to the water. That one keeps it on dry land. And then that planning now becomes very much a part of this the expected consequences of action, where there are certain beliefs that are held with sufficient precision that if they're violated, they will also become surprising, like not getting back into the water. So if my plans are underwritten by certain prior beliefs about the consequences of action, there is going to be a part of the surprise, or the expected surprise, that is underwritten by the kinds of things I expect to happen to me, given I do this or given I do that. So what we've got is actually quite a complicated, a slight, if you like, refinement or nuancing of the imperative to minimize expected free energy or expected surprise, because we have to carve that up into two kinds of expected surprise. One is the epistemic part, which is resolving uncertainty and seeking information. But there's also another part, which is the avoiding surprising, unfamiliar, uncomfortable, outlandish states of being, which for a fish would actually be on land. But for us would be, we wouldn't expect to find ourselves underwater for a protracted period of time. That would be outlandish. That would be a surprising outcome, and therefore it would make that particular course of action, that path or policy, that plan, highly unlikely, as scored by my expected surprise. There's a beautiful piece of maths underneath this, which you can. Do you want to indulge me, or do you want to move on to your next question?
You can absolutely go for it.
Okay, so that sort of dual aspect to the expected surprise also refers to surprise itself. If you read surprise as the evidence for me or my model of the world that I entail. So if you're a statistician and you want to maximize the evidence for your hypothesis, and you've got a bunch of hypotheses or statistical models, and you want to score the evidence, what you are very mindful of is that evidence can be split into two bits in exactly the same way the expected surprise or the expected free energy can be split into these information gain and expected surprise parts. The epistemic and the pragmatic, sometimes called intrinsic and extrinsic value, or intrinsic motivation and extrinsic motivation. There are lots of different, depending on which field you're in, there are lots of different names for these two sides of the coin. The equivalent in straightforward statistics is complexity and accuracy. So the probability of some data given a hypothesis or model of those data can always be split into accuracy and complexity. And the game is to try and find the model or the hypothesis that provides the most accurate account of those data, that minimizes the prediction error of the data itself, whilst at the same time minimizing the complexity or maximizing the simplicity. So this is Occam's principle. And it's vitally important in both statistics and machine learning, because if you ignore the complexity part, then you will overfit your data. So this is a truism which is often overlooked in many fields, and I think at great cost, that to do good self-evidencing, either as a statistician or a person, you're in the game of finding the simplest explanations that afford accurate accounts of your lived world as accessed through the sensorium in the moment, making sense of these data that have actually been realized, that are at hand for you to play with. the equivalent when it comes to the expected data, the data I anticipate if I follow this action or that action, of that accuracy and complexity, now becomes ambiguity and risk, which is another way of carving up the teleology of minimizing expected surprise or expected free energy. So you're trying to minimize the risk of departing from your prior beliefs about the kinds of outcomes you expect to encounter and enjoy. So for the fish, there will be a great risk in pressing the button that does not return it to the water, because that outcome would be highly implausible. So there's a departure, a risky departure from its prior beliefs. And then the epistemic part becomes the ambiguity, and it's this part that resolves things like the dark room problem. This is the curiosity. The first thing that I go do when I enter a dark room is to turn on the light. Why am I doing that? Well, I'm doing that because now the information and the way that it is being generated by whatever is out there is now much less ambiguous, supplied to me in a much less ambiguous form. So darkness is very ambiguous. It could be anything out there. It could be a bed or a chair. There could be nothing there. I don't know. But as soon as I put on the light, then the data become much more informative, much less ambiguous. So it's just this, I find a beautiful symmetry between the pressure on statisticians and scientists to come up with the simplest, minimally complex hypotheses that provide an accurate account of everything they're trying to explain in the moment, given some data, and the imperatives for good behaviors that have this sort of risk and ambiguity. And you can sort of look at those terms, and what you get, you can rearrange those terms, but preserving that sort of dual aspect. And what it looks like is exactly what people on two sides of the Bayesian coin, when it comes to behavior, have known for a century, well, slightly less than a century. So on the one hand, you've got Bayes' optimal design principles. So this is the epistemic part. This is the ambiguity resolving part of this imperative to minimize expected surprise, that can be articulated in terms purely of the information gain. So that's the principle of optimum Bayesian design. So if I was a very, very good scientist, I would always do the perfect experiment that got me those data that maximally informed my hypothesis space. And then the other side, which is the risk side, is what is considered by people in decision theory, in particular sort of Bayesian decision theory, to minimize the expected loss or cost of some outcomes. So you put those two together, and then you've got the expected surprise or the expected free energy. So I find this sort of what looks as if these are dual imperatives to keep on the well-trodden road, the well-trodden path, yet at the same time learn as much as you can about the terrain through which that path is coursing.
Yeah, that's nice correspondence. I think the elegance seems to fall out of the we were talking about the simplicity of these tautological ways of thinking, and just the imperatives to survive it will trim the fat, I think, and bring in that Occam's razor type elegance to any life process. And so you prefigured this a bit with your mentioning the difference between viruses and us. But I'd like to talk about consciousness, because you've collaborated with a bunch of different people and written some very interesting things about consciousness. And my understanding is, your stance is the free energy principle alone isn't a theory of consciousness, but my impression from your writing on it is that you're kind of attributing consciousness to a mechanism of a kind of recursion, like modeling yourself to the point that you get a kind of a certain level of self-awareness, and that's the key thing.
Yeah, no, absolutely. Yeah, and you're absolutely right. The free energy principle, and indeed active inference, I don't think is at all a theory of consciousness. That's what Jacob Howe likes to say repeatedly, and I agree with it entirely. And I should say, yeah, I have written about consciousness only because I have been asked to, or my young colleagues are philosophers. I am not philosophically literate, nor do I know very much about consciousness research, but from the perspective of the sort of the physics of sentience, then the questions about different kinds of artifacts that may or may not look as if they were conscious, to different levels, usually reduces to the nature of the generative model that is apt to describe their behavior. And I think the biggest distinction is one which we have been talking about for the past half hour, which is, do you have a generative model which would be fit for purpose to describe a virus or an amoeba or a thermostat, which just talks about states of being and reflexively responds to bring those preferred states of being, realize them through this gradient descent in the moment? Or do you have a generative model that entertains the consequences of action which you would need to plan? Now, both are perfectly, you can find examples of very effective phenotypes, all around us. And, we keep referring to viruses, which is particularly pertinent at the current time. But the kind of generative model that would be entailed by a virus, which is great for the virus, would not be fit for purpose for us, and indeed existentially wouldn't allow us to stand out as defined by that kind of generative model. So what kind of generative model do we have that a virus doesn't have? And I think it's as simple as what we have been saying. It's a generative model of the consequences of action. Now that immediately tells you two quite sort of profound things, literally deep things. The first it tells you is that you now are equipped, or your body and your brain entail, a generative model of the future. Why? Well, because the consequences of action have to follow the action. So immediately you've got a temporal depth to your generative model, which the virus doesn't have and doesn't need. Thank you very much. But we clearly do have generative models of the consequences of action. So just being able to plan, or systems that look as if they are planning, can only be explained by an implicit generative model which has a temporal depth. The second thing that's the notion of planning brings to the table is that simply there being action means there has to be an agent. So immediately you're talking about things that have a generative model that at least have an implicit notion of agency. And then the question is, well, is the agency part of the generative model? So you can imagine, sort of quite sophisticated creatures that can certainly plan, but they don't necessarily have to have the hypothesis in their model that it is them doing the planning. So you can imagine certain kinds of endearing pets can certainly plan and place themselves to elicit certain responses to make you take them for a walk or feed them or whatever, and yet you may not necessarily ascribe to them a sense of selfhood. Perhaps they were lizards as opposed to kittens. So you don't necessarily have to have a sense that you are the agent in order to have a generative model which can predict various muscle sensations or various secretory consequences of internal secretions and interoception, in order to have a generative model of the consequences of one action versus another action. So that suggests that, from moving from the generative model of states of the world to paths and plans and trajectories through state space and the consequences of action, we now have a second move, that may be distinguished by the fact that this generative model now suddenly has become equipped with the hypothesis that it is me doing that, generating those consequences through some action. So now, mathematically, you have to ask the question, what licenses the additional complexity that would be implicit in adding another bit to your generative model? Before you were actually noting that there is, if you like, a certain efficiency inherent in minimizing complexity. And I think that was quite insightful and technically very important. So I just want to just briefly say, not only is that common sense in terms of having the simplest kinds of generative models are those generative models that will generalize to new data and new contexts. They will be statistically much more efficient. In fact, they'll also be thermodynamically much more efficient. So there are various theorems, including Landauer's principle, the Jarzynski equality, that enable you to show that the minimally complex models or minimally complex belief updating translates into the thermodynamically most efficient. So this is, it literally costs you a certain number of joules to change your Bayesian beliefs, to change your mind. So if you can minimize the complexity, which is basically scored by the degree to which the data now change your priors to your posterior beliefs, the amount you've changed your mind, it costs energy to move further, which is why minimally complex models, hypotheses, fantasies, explanations are those that require you to change your mind the least. So everything was nice and predictable. Your prior beliefs are perfectly adequate to provide an explanation for this. So this fundamental imperative that rests upon, again, I keep referring to this sort of dual aspect to good self-evidencing, accuracy minus complexity, risk plus ambiguity. That actually translates, that actually has an enormous implication when asking questions. What licenses me, say I wanted to build self-awareness, say I wanted to build a robot with minimal selfhood. It would be trivial to do. I would just put a particular belief hypothesis space, encoded in silico, where there was a hypothesis, I did that, you did that. And then all the message passing in my deep neural network or my active inference scheme or my belief propagation scheme would be fodder for or information for one hypothesis or another hypothesis. And that would enable me to test the hypothesis that I did that as opposed to you did that, and accumulate evidence for that, and my beliefs about whether I did that as opposed to you doing that would tend towards some posterior belief, and no, I did that. That was me doing that. So what I've done is build an artifact, just giving it the hypothesis space, just giving it the capacity to say, no, that was me, not you. Why would I do that if I'm trying to minimize complexity? Well, it's only licensed if I live in a world where that extra complexity cost that I've incurred by equipping, say, a hierarchical generative model with this highest level of I did that, or you did that, or another person, another kind of creature did that. If that pays its way in terms of the accuracy, if I can, if I live in a world where it is necessary to disambiguate between me and you, then that selfhood inscribed into the model by equipping it with a hypothesis that it can actually, these things can be caused by people, and that person can either be me or you, is only licensed in a world where that is worthwhile or is necessary to account for these data. So you argue yourself into a situation where, yes, okay, I can see that equipping a robot with selfhood would be licensed, and if I then use the free energy to optimize the model itself, or the Bayesian model evidence to do Bayesian model selection, I applied a bit of sort of evolution to natural selection to implement a bit of Bayesian model selection on my robot. That selfhood's only going to survive in particular worlds. What are those worlds? Well, worlds in which it's necessary for me to disambiguate whether you did that or I did that, which means that I have to live in a world that is populated by other things that are very much like me. Otherwise, it makes no sense. So you end up from a purely mathematical argument by saying, yes, there could be certain generative models that self-evidence and do so with the right kinds of models that actually contain a minimal sense of selfhood, or the ability to infer I did that and you did that, and implicitly there's an I-ness in that inference, a me-ness. That would be necessary, but only in situations where that disambiguation became important. And those situations are where basically there's lots of other things like me that could do the same kinds of things. So did I say that? Did you say that? When in communication, or when say from the point of view of a neonate, was that me doing that, or was that mum? And working out who caused what may be one of the most important hypothesis to resolve. But to resolve it, of course, you've got to have the hypothesis that I am a thing. So as me as subject and me as object, or you as subject and you as object. And then from that, you can say, well, having that hypothesis that has to generate an accurate explanation for the sensorium, how on earth does knowing that provide a more accurate explanation? And it may well be that it's not so much the things we predict, but it may be the things that we attend to. So this is a slightly subtle move here, but I think is probably one sort of putting on the table, because what it does is it sort of brings attention into the game, and that it may be that the reason for inferring agency may be really important when augmenting or attenuating various sources of information that will either confirm or disconfirm my hypothesis about what's going on. So technically that's usually mathematically encoded in terms of the precision or the negative entropy of various beliefs or various sources of information. Psychologically, that looks basically either as increasing the confidence or the predictability afforded to certain sorts of information, that would be attending to stuff. And in other situations, equally important, attenuating, in particular the consequences of action. So this is a well-known phenomenon in psychology called sensory attenuation. But notice that if I want to invoke sensory attenuation, which is basically ignoring the consequences of my own actions, so I can act first and ignore the evidence that I'm not acting before I've acted. If I want to deploy sensory attenuation as part of my inference, I actually have to have the hypothesis it is me acting. So, just almost for free, you get the kind of generative model that would support a minimal selfhood or self-awareness, if you recognize that there are certain there are certain ways of attenuating, augmenting information in exchange with others. And I'm thinking here about sort of communication as we're engaged in. While I'm talking, I'm actually attenuating my auditory responses to what I'm saying in order to be able to say it fluently, whereas you're attending. And then I will stop doing that. But I can only do that because I'm inferring it's my turn to talk and it's not your turn, which means that I necessarily have to have a minimal sense of selfhood. And there are lots of people who've taken that kind of argument beyond the motor domain of articulating dyadic interactions in communication through to communication with the body and interoception and sort of tying in the gut feelings and sort of Jamesian notions of senses of me, selfhood that is truly embodied, and sort of blending, if you like, this attentional aspect with the interoceptive aspect to give a fully rounded, at least conceptual model of the kind of generative model you would have to have in order to be to have a minimal selfhood. The next move would be, how do you know that you've got a sense of self? So I'll stop there. But then there's self-awareness has not yet emerged. All we have is a minimal selfhood that we use to deploy our attention or attenuate our attention and to infer agency. But I may not be necessarily aware of the fact that I have a sense of self. So I may not be self-aware. I'm just aware that either I can do stuff or you can do stuff. So there'll be layer upon layer, a nice sort of an onion or hierarchical structure to the kinds of generative models.
Right. And speaking of selfhood, one of the levers we seem to have that most directly affects it is the serotonergic psychedelics, that we're seeing a kind of renaissance in their therapeutic use. And I saw earlier this month that you'd called on the UK government to reschedule psilocybin to make it easier to do research with. And you also have this fascinating paper with Robin Carhart-Harris on a theory of psychedelic action called Relaxed Beliefs Under Psychedelics, or REBUS. Would you be able to just briefly explain, before we run out of time, how that fits with what the picture is there of how they act in the brain and how it fits with the free energy principle?
Yes, of course. And I'm mindful you said briefly, so I'll try and make it brief. So it actually directly follows on from this notion of attention, sort of greasing certain pathways, affording more predictability and therefore more weight to certain messages or prediction errors or free energy gradients that you think convey important information. So if you imagine a hierarchical generative model with multiple levels of abstraction, so the simplest, most elemental explanations live very near the sensory level of a hierarchical model, the sensory interface, the Markov blanket. But you can have a very deep model, usually cast as a sort of centrifugal architecture, so stuff in the center, usually hypotheses, narratives that last a long period of time, but much more abstract. The degree to which they are informed by or provide top-down constraints on the Bayesian beliefs held at different levels of the hierarchy, so the more peripheral towards the sensory level, depends very sensitively on the precision that you estimate, the predictability that you estimate of the various messages in the hierarchy. So put it very simply, if there's any imbalance between the precision of your prior beliefs deep in the hierarchy, your convictions, this is how narratives unfold, and the precision afforded sensory information, sometimes referred to as sensory precision, then you can see immediately that there's going to be a profound change in the way that your sensorium causes you to change your mind and generate new and different hypotheses about what's going on. And if certain drugs selectively act upon the precision at various levels in the hierarchy, you can see how easy it would be to dissolve the precision of your deep central beliefs and start to entertain intermediate hypotheses where most of the shape to your perceptual content is actually at a lower hierarchical level. So this would translate in terms of a preoccupation and an inability to attend away from the sensory aspects of your perception. At the same time, you now have, because you've reduced the precision, the rigidity of your prior beliefs, you now have the possibility to explore different hypotheses. And certainly, if at the deepest levels of the hierarchy there are these narratives that have the selfhood attached to them, sort of me as an agent, and an agent that sort of does this kind of thing. Those are the ones that are going to be dissolved and allow you to reconfigure those. So it's basically using drugs to understand hierarchical message passing in the brain in terms of the precision or the fidelity of the sensorium versus your prior beliefs, and just redressing that balance transiently with a drug, usually. But because you've done that once, you may discover hypotheses that you didn't previously had, or you may enable yourself to not be stuck in a rut because you've now seen there's another rut next door and another rut next door to that. So you can have long-lasting effects in psilocybin-assisted therapy, particularly in terminal cancer care, end-of-life care, where it is possible that you get stuck into a particular self-model, a narrative that has all these self-attributes, that I am a dying person. I would expect to feel like this and to behave like this, and this is, my prior beliefs are then realized through active inference. But there may be other ways of living in the last few glorious months of your life, which are not hypotheses that you have been able to access at this point. So sometimes you can dissolve these prior constructs and just allow an exploration of a landscape of hypotheses simply by flattening the free energy gradients appropriately through changing the precision or the slope of the gradients that cause the neural dynamics. Physiologically, that is just basically by reducing the gain or the sensitivity of particular neurons encoding certain things in a predictive coding framework. That would be prediction errors. These are exactly the effects of things like 5-HT2A drugs like psilocybin, and in fact, nearly every psychotropic or psychedelic drug or psychomimetic drug used in psychiatry and most in neurology are exactly these neuromodulatory drugs that don't change the firing, they change the sensitivity of neuronal firing to inputs, and thereby do this sort of gating, this precision gating or attentional selection or attenuation role. That is exactly what we were positing as the justification for having a selfhood in the first place, because that it's the top-down deployment of the attention that is the purpose of having these very high, deep constructs.
Right. Yeah, and I think when you use the free energy principle to think about how the organism operates, something I like about it is it suggests there's a real pragmatism in the approach. It deals with its existing niche, its existing models, and responds based on that. It's not like it has a God's eye view of what the optimal, perfect strategy would be. And so because it's very pragmatic in that way, I can imagine it accounts for why people can get stuck with models that are no longer serving them. So for most of your life, the idea that death should be avoided at all costs is a good model. But then if you're faced with certain death, at that point, that piece of evidence is struggling to update your model, but actually it'd be quite wise for you to update that model and embrace the certainty of your death.
Yes.
So it makes sense to me that it fits with this whole scheme we've been talking about.
Yes, yeah. I mean, many people do have to sort of grieve for that childlike immortality when they're facing death, and do so very gracefully. Thousands, hundreds of millions of people around the world, have to do that sort of relearning and find that new Bayes optimal explanation for the way that they're living in their world. I just want to that was an excellent point, and just technically, it's, I think, important in terms from a sort of the point of view of a psychiatrist, or indeed as a therapist, or just somebody who deals with other people. So there's something called the complete class theorem, which is a mathematical way of saying what you just said, which says that for any given pair of cost functions and behaviors, there are some prior beliefs that render that behavior Bayes optimal. So what that is saying, there is no optimal behavior. There are only prior beliefs, which is, I think lets you off the hook in many respects. There is no, mathematically, it is mathematically provable. There is no Bayes optimal behavior. There are just a certain set of prior beliefs you bring to the table to explain your lived world. You could argue that, of course, after a sufficient amount of time, those prior beliefs may not be fit for purpose for this lived world. I think that's a weak argument, because of course we're in charge of making that world. Even if I've got agoraphobia and I make my world just my house, then my priors are now perfectly fit to explain this world, because I'm not the kind of creature that goes outside. Now, you may not think that's terribly functional, but from the point of view of the complete class theorem, this is a beautiful illustration of complete, Bayes optimality in so-called pathology. And there are related arguments for depression as well, that it may actually, in the longer term, be completely Bayes optimal and functional in terms of this sort of tautological existential view of the free energy principle. There are evolutionary arguments, at least, that appeal to the free energy principle to say why we are prone to depression, and how depression has survived natural evolution and selection. So, I think it's a really important point when it comes to sort of thinking about the way that you make your mind up about the world and the way that I do. Well, they'll be completely different, and both of them will be Bayes optimal for you and for me.
That's a very reassuring point to end on. Well, thank you so much for your time. I've really enjoyed this.
My pleasure. Thank you very much for talking.
And is there any way you would send people to, like, do you have a personal website if they want to look into your gigantic list of papers, or should they just search you on Google Scholar? There is a really interesting, it's probably a bit technical, but I mean, possibly not actually. There's some a GitHub, or GitHub, I'm not sure how you pronounce it, website's been assembled by a PhD student who was at Edinburgh, by Baron Millage. If you want, I can email you that. I didn't do that, but it's much better than anything I could do. And he's just annotated all the key papers, but crucially sort of bunched them by sort of theme. You can look for machine learning bits or sort of ethology bits. So I think that's probably the best resource. Yeah, that'd be great. I'll put a link in the description.
Okay, I'll send you. Yeah.
Perfect. Thanks again.
Okay. Cheers then.